Good morning. April is here. Good morning, April.
Good morning.
You found Jackson County's new radio station, KORG. You Falls Memphis.
Let's see, what shall we talk about? Well, let me set something up here just to kick things off. Let's find a good graph. While everybody's wandering into the building, let's find some parabola. Let's see. How about x squared minus 6x plus 13? Whoa, that is a crazy scale. Zoom square. There we go. And let's pick a point. This is kind of a neat problem. Let's pick a point out here called the point 82. Eight, nine. Now let's go 4. All right, that'll work. Put a label on that guy. Okay, this is kind of a cool problem. And yesterday, just by coincidence, everything we looked at was kind of a maximum. But today, let's look at a problem that's a minimum, because they're actually just as good. Projector mode. So my question to you is basically, what's the closest point on that red parabola to the point 84? Now that's just an interesting question, but on another note, given that objects fly through space in either elliptical orbits or parabolas though, when they come into contact with whatever's gravitationally pulling on them, and I'll make a copy of this and show you what I mean in a second, they'll get bent in space and then actually travel back out, and you'll sort of never see them again. So, kind of an interesting way to think about this question is to think about it as, we're at the Earth, we're at the Earth on 8-4, and when is the closest point that comet or whatever it is we're looking at in space is actually going to be to us. So there's a number of ways to kind of spin this question, but that's just kind of an interesting thought. But it's kind of a cool problem, and so let's just grow our skills with optimization. Really, we just need to practice today. So what I'd like to do is just, again, elaborate a little bit on what I just said, but then maybe give you some thought time before I just launch into this. That's lovely. And you have a question in your assignment about this too, which is good. So this is good prep for that. But the basic question is just, what's the minimum distance from our point 84 to the parabola? And again, just to elaborate on what I said a little bit, if for instance, the sun is right here. Maybe you remember from your Math 111 studies that when something in space is gravitationally pulled around it, so this might be the flight, as I said, of like a comet, that gets into the gravitational field of the sun, if you will. It's kind of out here just cruising along straight through space, and then suddenly it gets into this place where it's being pulled on by the sun, and it actually gets pulled and whips around the corner and then just takes off out into space again and never comes back. But we're also in the gravitational field of the sun, but we're in orbit around it. We're not coming in contact and then leaving parabolically. We're actually in orbit. And so, the question might be, what's the best night to see this thing, or when are we going to be the closest to it? Occasionally you hear that kind of stuff in the news when something astronomical is happening. And so you can kind of tell that it's like right in here somewhere. That's the closest point to the parabola. But in this case, we're trying to optimize, minimize in this case, not maximize, but minimize. What's the minimum distance between those 2 points? And so again, I just want to give you a second to think about it. Like how could you set, the basic thing I hope you took away from yesterday was I need an equation, which I got to make for myself, hard part, that I will then take a derivative and set equal to 0, because setting a derivative equal to 0 is what tells you maximums and minimums. And so the hard part here is, how do I make an equation? And again, in a sense, yesterday was, I don't know, maybe not a lot of help, because this is a brand new question. They're all brand new questions. So, is there some way that I could set that up? So I'm just going to give you a few seconds to think about it. So I'm going to say, I don't know, it's right there. That's my guess. But the problem is I don't know what to name it. And as I said before, do you have to know calculus to estimate that point? Notice it's pretty darn close to where I just drew it. I'll be surprised if it's off by much at all. So if your goal is just to kind of get an estimate, well, you're done. I mean, what do you think that looks like? To me, it looks like 4.2. I guess I'll even write it down. Estimate 4.2, and I guess that'd be 5. I'm going to say 5.4. There's my estimate. Done. If all you need is an estimate, you're done. You don't need calculus. But let's see what we can figure out. Well, I'm going to give this a name. I'm going to call this the point AB, since I don't know what it is. And then the question is, can I set up, well, what is it I'm trying to do? Well, I'm trying to minimize the distance. The key word there is distance. How do you find the distance between a couple of points if you know their coordinates? How do you find the distance between those? Do you have a formula in your mind, or better, could you just make the formula for yourself because you understand geometry a little bit? I'm going to make it for myself, because my guess is you don't have the distance formula memorized. But as I'm often trying to point out, you don't need to have things memorized in math. You can build them for yourself like a tool. And so distance formula that's kind of formally taught, that you would have seen sometime, but as I said, most likely forgotten, is based on the Pythagorean theorem. And all you have to know is the two legs of the right triangle, they're called. And of course, I can get those because to get out to this point, I had to go out 8. And to get out to this point, I had to go out A. So then this distance right here would have to be 8 minus A. Isn't that how slope works? Slope is y minus y over x minus x. Like, that's where the minus sign comes from. And similarly, to get to this point, I had to go up 4. And to get to the other point, I had to go up B. So I guess that distance would be B minus 4, or 4 minus B. Which is it? In my case, I did it the way I drew it. In other words, I took the long one minus the short one. Notice with respect to slope, you can't do that. You can't do that with respect to slope. You got to be consistent. You got to take, in my case, I took the number 8 minus a. So I took the purple point first. Well, I can't call the second one 4 minus b. B minus 4, I'd have to call it 4 minus b. But this is what you do for slope. But then what is it I do to those two terms to get the distance? You tell me.
We'd have to square them and then take the square root of the sum.
Yeah. I have to take those two, stick them into the Pythagorean theorem. And so I'd have to take the 8 minus a, whatever that distance is, and square it. And the b minus 4, whatever that distance is, and square it, and add them together and square root them. And that would give me distance d. And notice in this case, it's kind of interesting because I'm squaring it, it won't make any difference. In other words, if you subtract backwards, one way you subtract, you get, say, minus 8. The other way you get plus 8. Well, because you're going to square them, it actually doesn't make any difference. And and this is what the distance formula is. I'm going to erase this, but the distance formula says distance equals the square root of x minus x plus y minus y, and they're squared. And in a book, they would even go to the trouble of saying this is x1 and this is x2 and this is y1 and this is y2. And so it's just Pythagorean theorem. And so the cool thing is I've forgotten that formula, but I can just make it for myself. I can just draw pictures and make it for myself. I don't need that. So that's the formal distance formula. Okay, cool. Well, it's that equation then that I've got to minimize. I've got to take its derivative. So, but I don't know, how do I take the derivative of that? And again, one of the things we did learn or did see yesterday, and the most prominent sort of obvious place we saw it was with the cylinder. In other words, we had an equation that had a v, but then on the other side, it had a pi and an r squared and an h. And we didn't really like the fact that there were two different letters over there, because we really needed to find like dv or v prime, or maybe dv We don't like the fact that there's two different letters over there. And today it's no different. I'm staring at two different letters over there and I'm thinking that's not good. I sure wish one of those would go away. Because right now I'm going to have a really complicated derivative. So, but aren't A and B related to each other? How are A and B related to each other in this problem? Can you just pick A and B to be anything you want? There is an enormous hint. In other words, another way to look at B is to say, well, that's just f of A. In other words, if you pick A to be, say, well, as I did 4.2, then you'd actually have to plug in 4.2 into this equation to get y. And so it sort of doesn't make sense here for me to guess both x and y, I mean, because it has to actually work in this equation or it isn't even on the red graph at all. So the point is there's another way to write B. So B then, so as kind of a side note, B could be equal to, well, if I plug it in, a squared minus 6a plus 13. Do you agree with that? Or I could say, perhaps f of a is what you would get. And when you get done, hey, that's B, that's the y coordinate. So what I'm saying then is if I took this piece of beauty right here and replaced it up there, then I would have an equation with only D's and A's in it. Now, how did I know that I want an equation with D's and A's? not D's and B's? The answer is, I don't care. I just need an equation that's only got 2 letters in it. So now I can say my distance is equal to, and maybe I'll multiply this out. Boy, this sounds terrifying. And I'll write it out first. So get 8 minus a squared plus b minus 4. So since this is a squared minus 6a plus 13 minus 4, that'd be a squared minus 6a. 13 minus 4 is 9. So there's my equation. And so if I can take the derivative of that, and since this is kind of step 1, I found an equation that relates the distance to the location of A. As per yesterday, though, let's see. 8 minus A, 6, negative 9. I wonder if you know what I'm doing right now. You don't need calculus to do calculus. So let's see, did I actually, is that the right equation? X, 8 minus x, 6a plus 9. Wow, it's a miracle. It is the right equation. So that g of x equation is d. Does that make sense? That's d, and I actually don't know. Can I get away with that? Can I call it d just to make it a little clearer? Apparently I can. So if a is 2, and let's go ahead and graph that just because it'll look cool to do so. If I graph the point A, d of A, actually I think I need to say f of A for that. So there's where I am on the graph. Right now I'm at the point x is 2, and I notice I never figured out y is 5. I just plugged it in. I'm at this point. And so if I haven't screwed this up, do you agree that 6.08 d of A, that's the distance. I just plugged A into that expression. The distance between 2, 5, and 8, 4 is 6.08. So assuming I didn't make a mistake with that shape, but watch the distance get smaller and smaller if I didn't screw this up. See how it's getting smaller and smaller? I'm getting closer and closer to the 0.84, 4.60, 4.4, 4.35, 31, 29, 26, 24. Oops, now it's going back up again. So 4 point, let's see, 17, 14, 13, 12, 11, 10. 0.0706. See how it seems to be working? Do you see what I'm saying? It seems like the distance between the 2 points that I found is working because that really does look close right there. And if I go further away, now it starts to grow and get bigger and bigger and bigger. So again, do I need calculus to get the answer that I need? The answer appears to be no. So that's 0.625, 0.64, 0.622. Rounded to 2 decimal places, that's the closest one I got, 4.0622. So it seems like my distance formula that I made is working because that looks close to the purple point P, and and it's about what I guessed it would be. So, can we do better than that? Well, if I take the derivative of that statement right there and set it equal to 0 and solve it, apparently I'm going to get a, or the x coordinate of my point, apparently I'm going to get 4.23. That's what it just showed a second ago, I think. The question is, can you take the derivative of that? Well, in that form, that looks awful messy, so I'm going to clean it up a little bit. Let's see, I got 8 minus a squared, that's 64, minus 8a minus 8a, so that's minus 16a, plus a squared, so there's that term. And then, woo, this one's going to be ugly. A squared squared, that's even worse. So a squared squared would be a to the 4th, and I'd end up with a minus 6a cubed and a minus 6a cubed, which is minus 12a cubed. I'm trying to go faster. It's probably dumb. I'm a little concerned that I'm going to screw this up, so I better slow down a hair. So let's see, a times a. So then there's, now I got my a squared terms. So there's a 9a squared and another 9a squared for 18a squared. But then there's a minus 6a times a minus 6a, which is 36a squared. So it's 54a squared. Whew, dangerous. And then there's minus 54a and minus 54a, which is minus 108a. And finally, 9 times 9 is 81. Boy, I hope I didn't screw that up. So I don't know, is this easier? I'm thinking it's going to be. So d equals, let's see, what's my terms? I got an a to the 4th. I got minus 12a to the 3rd. I've got an a squared and 54a squareds, which is 55a squareds. And I got a minus 16a and a minus 108a, which is minus 124a. And finally, I've got 81 and 64, which is 145, I think. And that's all raised to the 1/2 power, square root. So now I think, all right, let's take the derivative now. I can do this. So either what you might call dA, the derivative of d with respect to a, or just you might say d prime, then would be power rule for the 1/2. Everything inside stays unchanged. I'm in a lazy mood, so I'm going to copy it. And the exponent, you subtract 1 from it, and then I multiplied by the derivative of the inside. Well, that's terrifying. 4a to the 3rd minus 36a squared plus 110a minus 124. So it's multiplied by all of that. So that's my derivative. And now I've got to set all that equal to 0. Now that looks worse than it is, although it's still pretty bad. Because if I was to kind of rewrite this a little bit, I could say that d prime is equal to, well, what's on the top, what's on the bottom? The 4a cubed minus 36a squared plus 110a minus 124 is on the top. That 2 is on the bottom, and then there's a bunch of junk to the 1/2, except for if I move it down, it becomes negative 1/2. So all that stuff. You agree with that algebraically? And so what I'm after is, well, a minimum and a maximum. Feels like time to change colors. Minimum or a maximum happens when d prime is equal to 0. So I need to set this thing equal to 0. And that's where it's actually not so bad, because then I say, oh, okay, well, if that fraction is equal to 0, I could just multiply both sides by the square root and the 2. And all I really have then is just the top is equal to 0. However, as you most likely know, that's still not good, because we got a cubed equation and we can't solve cubed equations. How do we solve cubed equations? We don't have a cubic formula. We have a quadratic formula, But we don't have a cubic formula, so how are we going to solve that?
I was wondering with these why we can't add 124 to both sides and then factor out an a. So then we have when a equals 0, then that would make everything, and then the quadratic on the inside. But that seems too easy because that looks like it would work for everything, right? So I'm guessing there's some reason why not.
That would mean
So
it didn't equal
what Logan
0.
is saying is, couldn't we just get rid of the 124 by adding it to the other side, and then the terms on the left side would all have an a in them, and so I could factor that a out, and so great, why can't I just use the quadratic formula now? And you can't, but does anybody see why not?
Because now it's not equal to 0.
Correct. The fact that it's not equal to 0 is the problem. Like, it seems like a small thing, but when this is equal to 0 on this side, then you can say, hey, look, junk times junk equals 0. Well, then you can say, okay, well, then 4a squared minus 36a plus 110 could be equal to 0. But if it needs to be equal to 124, now all of a sudden you can't think of those two statements as independent of each other. Now, if you choose something for a here, then whatever you multiply it by over here, you're going to have number times number. Then now that's got to be 124. So you can't treat those two independently. And so that seems like an easy way out, but it actually isn't. Like, it's got to be equal to 0, or you really can't make any progress with it. So if that 124 wasn't there, we could solve this problem by doing what you said, because it'd be equal to 0. But if we add it to the other side, that's a deal breaker. So
Okay, got it.
very good thought. That's kind of one of my problems with math, is like, you just get told the first time you're using the quadratic formula, you just get told, here's how to solve this. And then you just go do it, and you're just hanging on for a ride, and you never really have time to think, like, why do I have to do it that way? Or, why can't I do this? And that's part of calculus, in my opinion, is just to slow down and ask all those questions. Well, unfortunately, you can't solve this. Like, there isn't a way, except for cheating. What do we do to cheat to solve a cubed equation in the world you live in with some technology?
Use a calculator for Desmos.
Yeah, you got to graph it. So when you graph it, you're graphing not equals 0, but equals y. But then you're looking for y is 0, remember, and where y is 0 is on the x-axis. And so if I graph that as y equals all that junk, then I can just see where does it cross the x-axis, and then I'll know what x values give me a y of 0. So 4, negative 36, 110, negative 124. What else was in that? 36, 110, 124. Was that it? Was it plus 110x? I think it was. So there's only one answer. Notice again, it's kind of cool just from, see the little hoop-de-doo in it. Like, that's still a cubed equation. It doesn't have the nice S turn in it, if you will, but it's still obviously a cubed equation. So it only has one answer, and that makes sense. Is there two places on this curve that would have a minimum distance? The answer is no, there's only one. So it sort of doesn't make sense that's the case. And so if I go here again, Desmos is kind of cool because it sort of intuitively knows you might want to know that. So there it is. And so I couldn't solve this algebraically. Again, to me, this isn't a good test question because I'd want you to be able to do the quadratic formula. But it's actually weird how complicated this question is. In other words, like, to answer what looks like a simple question, when's the closest place I'll be able to see this comet as it flies around the sun? What night will that be? You ended up having to solve a cubed equation to do that. We had to use calculus. We had to know just think back on all the stuff you've learned. We had to write the equation for ourselves based on the distance formula in algebra and Pythagorean theorem. we had to take a derivative, which involved the chain rule and the power rule. And we set it equal to 0 and started doing algebra. And we had a cubed equation to solve. I mean, this is like everything you've ever learned about advanced math. I mean, minus some trigonometry. So cheat 4.235. So cheat with the graph, and A is approximately 4.235. And so, of course, I could go back now and say to the original problem and say, you know, what goes with that? F of 4.235. I mean, my original equation was x squared minus 6x plus 13. So I can find the y that goes with it. So if I quickly do that on my calculator instead of wimping out, I could go back to Desmos and get it to answer this. It's just that I'm going back and forth. So I'm going to type 4.235 into that equation. So it'd be squared and then minus 6 times 4.235 and then plus 13. And I got 5.525. So the closest point is that ordered pair. That's kind of cool. Rounded however we choose. And I think that's what we saw a second ago, isn't it? I mean, I wasn't really paying attention. So now that that work is done, I can turn that off and I can turn the graph back on. So yeah, 4.2, 5.5. Apparently I got it right. So the calculus agreed with, well, just us tracing around on it. Well, what if at the maximum? What's the maximum point? How come we didn't get a maximum answer?
Because the graph goes on for infinity.
Yeah, it actually goes up forever. So there isn't going to be a maximum. It's going to be kind of an undefined maximum. And so that's kind of interesting. But if this was a circle or something, wouldn't there be like a minimum and a maximum? That's kind of interesting to think about. But kind of cool. It's kind of a cool question, I think. Again, it has a little bit of practicality to it, I think. So you may remember, just a side note, but how many answers from what's the fundamental theorem? I mean, that's an amazing statement. The fundamental theorem of algebra. What does the fundamental theorem of algebra say about a cubed equation?
There's 3 answers.
Nice job. There's 3 answers to it. And so in our case, based on the graph, we saw that one of them was real and 2 were imaginary. So in a sense, the maximum, there's 2 maximums and they're both imaginary. Why would there be 2 maximums? Well, the graph had 2 peaks that took off. And so they're both kind of infinity, if you will. And so, you know, perhaps that's why, but they're imaginary because, you know, you're not going to get something that's real. There's no way, it doesn't stop. And so the answer is really infinity. And so that's just kind of cool to think about. Fundamental theorem of algebra says that cubed equations have 3 answers. And so we found out that in this case, 1 was real and 2 were imaginary. So we didn't really care about the imaginary one. How's your brain? Is it in pain? Brain pain. Incidentally, there is a question like this in your assignment, but I'll be very surprised if they didn't make it up in a canned sort of a way so that you don't have to solve a cubed equation to do it. And I need to do the same on a test. I mean, I got to make these up a little more carefully. In my case, I just made up a random parabola and a random point. And you can also probably picture that if it was worse, like what's the closest point to this cubed equation or to this sine wave or something, maybe the equation would be even worse. But I guess I just want to remind you as you kind of leave algebra that, you know, as an expert in algebra, that there's many equations that you need to solve as a part of, and this happens in our engineering classes sometimes. So it's, you know, focused on reality, whereas we're focused on theory in this class. But there's many equations you can't solve. And in the real world, you don't want to solve them algebraically anyway, because you're going to make a math mistake. And so if there's a way to cheat and just graph it and solve it, that's what you do, because it's quicker and more accurate and sort of guaranteed not to screw up. All right. I do want to give you sort of a bunch more time with this question. Let's say this. Minimum surface area required to build a cylinder of, I don't know, 680 cubic centimeters. And this is the kind of thing I would not want you to have memorized for a test. And so if this was on a test, I would tell you these things, like the volume of a cylinder is pi r squared h. We happened to see that yesterday. But the surface area of a cylinder is the top and the bottom, which would be 2 circles of pi r squared, plus the area around the sides, which is 2 pi r h. And of course, maybe it's helpful to have a drawing of that. So the only thing I want you to think about before I shut up and give you some think time is just, a second ago we said, hey, what's the minimum distance? And so we said to ourselves, okay, well, then the key is, what's an equation for the distance? Because that's what we're trying to minimize. So whatever it is you're trying to maximize or minimize, that's what you need an equation for. Well, in this case, I'm saying, what is the minimum surface area? So you should be thinking, aha, this is the equation that I need to take the derivative of. And you already have it, like it's given. Last time we kind of had to make it for ourselves, but it's like, there it is. But the problem is, as I said before, especially if I kind of get rid of this A here, so it doesn't look like it's 2 different letters, that equation's got 2 unknowns on the other side. It's got R's and H's, and really that's kind of the problem. I really, just like last time, I don't want it to be D with A's and B's on the other side. I don't want this to be S. I don't want this to be S as a function of both R and H. Yuck. I don't really want that. I need it to be either S just as a function of R or S as a function of H. I'm fine with those. I can take that derivative and set it equal to 0. But I can't set the derivative equal to 0 if there's too many letters in it. And so, anyway, think about that. I'll give you some think time. And think, this problem wouldn't make any sense if we didn't design. And you should see this as a very practical question, like somebody's making soup, selling soup, and so they say, all right, I want to package 680 cubic centimeters of soup in that can, or some product you're selling, whatever. So, you know, go build. Minimum surface area here is kind of code for build the cheapest can you possibly can. And so this is a huge business application. This is more practical than most of the questions. So if I don't give you the size, then, you know, what's the minimum size can? Well, it's teeny. It's like hardly one at all. Well, I gave you a minimum size. So how does that help you with our conundrum down here, that's what you need to think about.
I guess wouldn't you want to make whatever equation you have like equal to or a little bit bigger than 680 centimeters squared or cubed?
Yeah, you are stuck with that. So the idea is you can't just pick R and H to be anything. Whatever R and H turn out to be, when I put them in here and here, then this better actually be 680. So you can't just have R and H be anything you want. So that's kind of your limitation, certain volume. But does it make sense that you could have sort of a small R, which might make your can look like this? It might be like a straw filled with soup. Small R, but as a consequence of needing a certain volume, it's going to have to be really tall.
I have a thought. Couldn't you solve the volume equation for like one of the variables and then replace that variable in the surface area equation?
That's exactly right.
Like solve for H, so it'd be 680 divided by pi r squared, and then replace the H with 680 divided by pi r squared, and then solve S as a function of R.
Exactly right. So the thing you need to see is if you chose a large radius, then you're going to have more like a cat dish. And there's all kinds of sizes. There's all kinds of sizes of cans, tall, skinny, and short, wide, and everything in between that would package 680 cubic centimeters. But calculus comes in saying, well, that's great. You can design it any way you want, but this is a business. And so we want to make the can that's the cheapest possible. And I'll elaborate on this, but one of your questions in your assignment, which is actually really good, is even adding money to this and saying the sides cost a certain amount of money and the top and bottom cost a certain amount of money. And so let's do it as cheaply as possible. But you can see this is the same thing, like it's the cheapest surface area possible. And what Andrew said is right. In other words, if you take that 680 equals pi r squared h, which is a limitation on this problem, a constraint, if you will, then couldn't I solve that for h and then replace h in that equation, in the S equation? Or perhaps solve it for r squared? I don't know which one makes the most sense. As I said, it really doesn't make any difference. This looks easier to solve for h. And up here, I see that I've got an r squared and an r. And when I look here and I see that there's an r squared, I think, oh, it wouldn't be hard to solve for r squared. And I could replace it with r squared. But then there's an r, which means I'd have to take the square root. So for me, it feels easier. And again, I want to give you a chance to get a little ahead of me here, but it feels easier to take 680 and divide by pi r squared and say that's equal to h. And then I could send this up here and replace h with that statement. And now I just have s's and r's. So that would result in this equation, surface area just as a function of r. So get ahead of me. Can you write that out? Can you take its derivative and set it equal to 0? That's the essence of all of these questions. An equation that I'm maximizing or minimizing, in this case, minimizing.
So the S equation is for surface area.
Yeah.
Oh, okay. I'm sure you were clear about that. I was just getting a cup of coffee.
Glad you asked. Notice there's some nice canceling that can happen there.
Yeah, this leaves 2 times 680. Well, squared. Wait, no, 2 times
2 times 680 over R. Yeah.
So what was that? 1360. Pi's cancel, and there's just an R left on the bottom. So that's an equation I can take the derivative of and set equal to 0.
So basically, when you set it to 0, it's going to tell you your max and your min of that surface area, of the potential surface area with 680 cubic centimeters, correct?
That's right. So the limitation of 680 is in here now. That's the thing that's kind of cool. It's in here. And so when I set this equal to 0, and again, the interesting thing is I don't know if I'm going to get a maximum or a minimum when I do this. Maybe I'll have to graph it to look at it. Because I don't know about you, but when I look at that equation right there, if I think of this as y equals 2 pi x squared plus 1360 over x, I think, I don't know what that graph looks like. That's really weird. It's not a parabola. It's got an x squared in it, but it's not a parabola because there's 1360 over x. And so, you know, remember, calculus cannot tell the difference between a maximum and a minimum. You can cheat and look at the graph, or you can get the second derivative involved. Remember, second derivatives tell you concavity. So if it's concave up, then that means you just found a minimum. If it's concave down, that means you found a maximum. And so I'm not really sure. Just because this problem said find the minimum doesn't mean the first answer you get is a minimum. Like, you got to think about that a little bit. And again, chapter 3 is such that you should be able to look at this and say, oh yeah, I know how to take a derivative of everything. But that still requires practice. I mean, are you stumbled at all by 1360 over R? Like, how do I take the derivative of that? Is that weird?
Well, wouldn't you use the reciprocal rule in that situation?
You mean move the R to the top and call it 1360 R to the -1?
Yeah.
Because that would work. Or you can say, well,
basically 1 over a function of x equals negative the derivative of x over the x squared.
yeah, so you'd either leave the R down there and say, oh, I guess this is a quotient rule problem, or you could move it to the top and make it R to the -1. Right now it's R to the +1. So whatever one you like.
I think R to the -1's easier.
Yeah, it gets away from the quotient rule. Quotient rule is kind of ugly, so I'm inclined to agree. Although in this case, quotient rule is the derivative of the top, which is 0 times the bottom left alone. So it's like part of that quotient rule is going to go away. But I agree. I'll do it by moving R to the top.
Then wouldn't you still have to square the R on the bottom?
Yep. But then there'll be an R on the top and an R on the bottom, and they'll cancel.
Oh, okay. Yeah. Duh.
So again, it's good practice to say, could I get the same answer both ways using the product rule or the quotient rule? If you're not sure, then you should be doing that. That's what makes you good at math. So check your derivatives. I'm going to do it now. So DSDR, remember what that means, like the language of calculus, because this does come up in later math classes. That means, how is S changing when I change R? In other words, how is the surface area changing? Is it getting bigger or is it getting smaller? How's it changing if I change R? If I make R a little bigger, I make R a little smaller, how is S changing with it? Notice this isn't ds dt. We're not talking about the speed at which the surface area changes based on the speed of how R changes. We're not talking about speed here. We're just talking about changing R to see what effect it has on S. And when there's no change, then that means we found a maximum or minimum when there's no slope. So whether you call it DSDR, whether you call it S prime, then you say, okay, great, that's easy. R squared, the 2 comes down front, and I reduce the power by 1. So now it's just R. Same thing over here. Bring the -1 down front. So now it's minus 1360. And then it's R to what power?
-2.
Good. Subtract 1. It'd be easy to screw that up and say it was 0 or something, but you're subtracting 1. So now it's -2. So derivative is found. So in a sense, first thing I got to figure out is an equation that I can take the derivative of. And that took a little bit of work this time. We had to mess with it a little bit. Secondly, can I take its derivative? And now can I set it equal to 0 and like survive the algebra? So let's see if we can survive the algebra. So when is 4 pi r minus 1360 r to the -2 equal to 0? Well, I find myself thinking, I don't like negative signs, so I'm going to add that to the other side. So it's positive 1360. And then I don't really like r to the -2. So if I move it to the bottom, it'd be r to the second. At least I can see things that I understand now. And then I think I don't like fractions, so I'll multiply both sides by r squared. So I've got 4r cubed. And then I think, oh, that's not good. Another cubed equation to solve. Is that weird that a cubed equation came up here? But fortunately, there's no r squared term and r term, so this isn't so ugly. And so I can solve this for r. I just have to divide by 4 pi and take the cube root. So fortunately, I can just survive algebra here. So again, what's interesting about this is I still don't know, is this a minimum or a maximum? I just know that it's a place where the slope is 0. And then I also noticed there's only one answer to this. There's the other 2 imaginary answers to this. There's only one, because r has to be positive here to give us positive 1360. So unless r was an imaginary number, which is where the other 2 answers would be. So there's only one answer to this. So let's see if r cubed is equal to 1360 over 4 pi. Then r would be approximately, and of course I could write it exactly, but I'm just going to figure out on my calculator what's 1360 divided by 4 divided by pi. And I got 108. Now I'm going to raise that to the 1/3 power. That's easier than taking the cube root. And I got 4.7655. And I think we were working in metric, so this is centimeters. Radius is a distance. That's centimeters, not centimeters cubed. It's a distance.
Would that be plus or minus 4.7655?
No, because if it was negative, when you cube a negative number, it's still negative. So negative won't work here. So it has to be to the 2nd power for there to be a plus or minus answer, or to the 4th power. It has to be to an even power in order for there to be a plus and a minus answer. And of course, even if there was a minus answer, radius can't be negative in our case, because practically radius would have to be a positive number.
Okay.
Good questions. So I wrote an equation, number 1, I took its derivative, number 2, and finally I solved that equation, number 3. And I think I have, and I'm not sure, I might have made a math mistake, but I think I actually have the answer now. And so, you know, again, my question just in a practical sense is like, what does this thing look like? Is it tall and thin or short and wide? Interestingly, go ahead.
When you were saying if we know whether or not it's a minimum or a maximum, I mean, I'm kind of assuming this, but is it possibility like I'm assuming that number is a maximum because like maybe the minimum is something that's just unrealistic due to the application, but then it would still come out in the math, right?
Well, it turns out that, does it make sense if you made this the top of the circle infinitely small? So it's like just the teeniest circle ever, infinitely small, that then this thing would actually end up infinitely tall because it still has to hold 680 cubic centimeters. So if you made the top infinitely small, then the sides would be infinitely long, and then in which case you'd have an infinite amount of surface area. So there actually isn't a maximum answer to this. Or if you went over to this example, could you make this thing infinitely wide? It's just getting wider and wider and wider, but then of course it would have to be really short. But notice the top is this huge circle. So if you made it infinitely wide but infinitely skinny, it still has an infinite amount of surface area. So there's two imaginary infinite answers. There's two imaginary maximums. This one's a minimum. Now I could graph it to see that.
Okay, that makes sense.
Well, also, wouldn't the fact that we used the 680, which is our limit, create this? Because if we didn't have that 680, we wouldn't have had a value to create this value. So we applied our limit already.
Yeah, without a limitation on our surface area or volume, without some kind of a limitation, then there'd be no limit to the sort of the size can we could design. And so it makes sense that this is a minimum just logically is what I'm saying. But you should graph this. Like go back to, remember, you don't need calculus to do calculus. If you graph that equation right there, if we haven't screwed up, and I'm not going to do it this time, but if you graphed it, you should see a minimum at what we just figured out at what was at a second ago. And again, that's an equation you probably don't recognize. I don't. So, what's that thing look like? So all I'm saying is it's cool that logically it would have to be a minimum because there'd be a minimum surface area. You can't have you can't have 1 square centimeter and somehow make a can big enough to hold 680. There's no way.
Yeah, because if we didn't apply that limit, it would be 4 pi r cubed equals 2 times v, which, because that's what 1360 is. So then you could have solved it for any volume, but we had a limit in place. So
that's right. And again, I'll encourage you to do this on your own on the side, but is this a minimum or a maximum? If you're sitting there saying that's a question. Well, if you went back and you took the second derivative of S and you plugged in 4.7 and you got a positive number, then that would indicate concave up right there, hence a minimum. So I'm not going to do it, but if we took a second derivative and we put our point in 4.7 or probably better 4.8, then you're actually going to get a positive number, which tells you, hey, the graph's concave up right there. Oh, okay, well, that means this is a minimum. So you can actually do this entirely without a graphing calculator, which is kind of cool, which is, what people did up until about 30 years ago. Nobody had them. And so you can sort of prove this is a minimum. Again, I would highly encourage you to do that because second derivatives are a little bit hard to kind of get your mind around sometimes, like what they're actually telling you.
Yeah, I've talked to some people that are older than me about taking calculus, and they're like, "Oh yeah, you got to use a slide rule," and I'm like, "What's that?"
Slide rule. That's awesome. So I am curious about a couple of things, and I want to show you something that's kind of neat here. But notice we found the radius. But let's go. Like, if you're going to build this, does it make sense you still got to go design it? You could be asked, what is the surface area? And you could also be asked, well, go build it. Okay, well, we know the radius, but we don't know the height. But remember, we have this equation here to give us the height. So I'm just going to copy it down below.
So now in a practical equation, like say we were building this, how much of a decimal would we go out to? Would it be like 2 or 3 decimal places?
Or very unlikely, unless you were
use like a 5 inches.
Holding something, worth $1,000 an ounce or something, like you wouldn't need to be that accurate.
So it would just be like 4.8 inches or 4.8 centimeters, call it a day.
Call it enough. Yeah, good enough. So I could find H then by plugging, and I want you to notice there's a relationship here. This is kind of interesting. So let's see. That means H would be 680 divided by pi times, well, our radius, which is 4.7655. I'm going to leave the whole thing in there. It's still approximate though, because I still rounded that off. But let's see what we get it for our height. If we do that, 680 divided by pi divided by 4.7655 squared, I got 9.53. Anybody notice a relationship between these two guys here?
They're pretty much one's twice as much as the other one.
Exactly right. And it turns out to be the case that it is exactly twice. If the height is twice the radius, and let me just say something. What would that look like if the height was twice the radius? What would is this a tall skinny can, or is this like the cat dish? What does it look like if that's the case?
I mean, it would be somewhere in the middle, really.
Yeah, think about what radius is. If you doubled the radius, isn't that the diameter? So the diameter and the height are the same. So this thing is kind of like a cube, if you will. It's like if that's how wide it is, then that's how tall it is.
It's a circular cube.
Yeah. One of the things that's kind of interesting about this topic is the most efficient shapes are in the middle. Tall and thin, total waste of material. Short and wide, total waste of material. What's the most in the middle you can possibly get? Well, that's trying to be a sphere. We limit it to say it has to have a flat top. But if you just said, what's the best shape you could possibly build that would hold 680, it'd be a sphere. You could actually use less material building a sphere. That's your best answer. Sphere is the best, and then a cylinder, because it's got some curvature, is the next best, and then a cube would be the next best. And so anyway, there's some interesting kind of theory there, both about product engineering, but also just about nature. If nature has a certain amount of water, it's raining right now, it wants to be in a sphere because of surface tension. It doesn't fall down through the air as a pyramid or a cylinder or something like that. It wants to equalize, and so the most efficient shape is a cylinder. So it's just kind of cool to note that 2r equals h. That always happens, actually, as it turns out in these problems, and you could kind of prove that if you wanted to. But we don't necessarily want to. Just a quick side note about your homework question. I'm going to go back to this. So I'm just going to go back here and say my open math, just as a hint. What if you weren't trying to minimize the surface area, but you were trying to minimize the cost? So now it's like, oh, okay, well, what equation am I minimizing? It's a cost equation, not a surface area equation. And so if it was cost, then you would say, oh, well, cost is based on surface area. But if the top, and this is what your problem, and this is somewhat realistic, it's kind of a cool question, but when you manufacture cans, either for pop or beer or soup or whatever, the sides are not as thick as the top is. The top has to be a little bit thicker. So basically the top is more expensive than the sides. And so what if the top cost 5 cents per square centimeter? Well, that's 5 cents times the area of the top and the bottom. But then the sides were only 3 cents. And the sides of this, uh-oh, is this true? Yeah, this is right. But the sides of this are represented by this statement over here. And so those are only 3 cents. And so does it make sense? That turns it into money. That turns surface area into money. If the sides and the top were the same, then it doesn't make any difference. We can do what we said. Oh, as long as you make the dimensions this, then that'll use the least surface area. And of course, that'll cost the least amount of money. But given that here we're talking money, it actually might not be this. It might not be the height is twice the radius now, because the cost got involved in this problem. And so that's kind of cool. So there's just a little hint. I want to do more examples so you have time to think today. But there's a freebie. Let's see. I could do this for like 10 days in a row. There's just so many neat questions, but I will say that's kind of one of my favorites. And I say that as more of a salesman for math than like a personal favorite, just because you can actually see somebody doing this. In the sense that, like, if you take a soup company like Campbell's, if they could save 1 square centimeter of tin on their tin can because they make bazillion cans, if that saved them 1 penny on that can, that would be millions of dollars. And so I guess I just want you to notice, like, this is a real consideration. Let's do one other example. Let's do and this is sort of a classic calculus example too, but I just finished a house plan with, which I've drawn very few of these before, but Norman windows are windows that look like this. They're a half circle on the top. I think they're ugly. And then they have a rectangular bottom like this.
I was about to say that same thing.
You think they're ugly too?
I do. I just, something about them. They don't look right to me.
I just don't like curves. I
think they look okay in like a church or on a stained glass window.
True. Yeah. Good point.
But like, if you're not going to do like stained glass, then I think square windows are much better.
Yeah. Has to be Gothic, like a Gothic building with stone and all that, and then it would look good. But
Doug, I might have to show you a picture of a house with curves that might change your mind.
I'd like that. So
okay.
There are some fancy ones. The one that I drew as an example, I should pull that up for you guys because you'd say, oh yeah, I'd live there.
All right.
I have one of those, except it's in ellipse and it's huge.
Yeah, and so there are elliptical windows, and there are circles that aren't half circles. They're actually like little chunks of circles, like an arch, but it's not half a circle. And so anyway, all cool stuff.
I feel like Norman windows have their place in architecture, just not in like square homes.
Yeah, not in Norman houses. Like, it has to be a fancy house. If it's a fancy house, it can look pretty good. But again, there's an interesting question here that involves calculus mixed into this, because I could say, if you think of this outside perimeter, because there's the perimeter of the window, which is, a piece of metal or steel around the outside, and that costs money. But then there's also the glass area in the inside, so you have perimeter and area. And so you can probably see that if this, and I'll just make this up now, if this is like W for the width, and this is H for the height, and we're saying that goes to there, you should be able to make your own perimeter equation for that. Notice the width of the window matches the diameter up at the top of the circle, but could you write an equation for the perimeter of this entire window based on that? I'm just going to give you a second to try. What's the formula using W's and H's for the perimeter of that window? Again, geometry knowledge, totally random, totally different question. But you should be able to do this, because isn't the perimeter, well, it'd be a W across the bottom plus 2 H's up the sides. And then what do you do to get the top? Somebody figured this out.
It would be half W, which would be R times pi, or half W squared times pi.
You're mixing up area and circumference. What's the circumference of a circle formula?
2 pi W.
2 pi R, or just pi.
Oh, pi W.
The diameter.
Yeah.
Oh,
Since our diameter is W, then it'd be W pi for the entire circumference, but we only have half of it. So it'd be a half of W times pi. Do you agree with that? Now, and notice it's like you got to shake the cobwebs out. You got to, I'm not giving you a lot of time, but it's like you have to go look that up online, double check some things. It's like, but that's speaking the language of algebra. Of course you don't remember it, but you should be able to go get it for yourself.
Yeah, I've been doing so many problems with area, it's like
Yeah.
kind of circumference in a while.
And while we're at it, there's an interplay here between area, just like in the last problem, there's an interplay between surface area of a 3D object and the volume of a 3D object. In this case, there's an interplay between area of the glass, letting light in, and the perimeter. And so what would the area be? What would the area formula be? Should suffer less for this one. I'm only going to give you a second or two. So you got a rectangle in half of a circle. I mean, I have to chop it. There's no formula for this shape. You have to chop it into shapes you do understand. Oh, rectangle in half a circle. Rectangles are length times width, or in this case, width times height. So there's the bottom. And then circles are pi r squared. So pi times r, but in this case, r would be, well, half of w. And then we need half of that because we only have half of a circle. I suppose I could clean that up a little. I guess that's pi w squared over 8, since it'd be w squared over 4 divided by 2. So it'd be pi w squared over 8, I guess. So again, these two things are related to each other. And so the two problems I could give you here that are interesting is, one is, what if you had only a certain amount of the leaded metal that goes around the outside? What's the biggest area window you could build out of it? Or I could say the other way around. You want a certain area, and so, what's the minimum perimeter? Well, in a sense, that's the question we just did. I gave you the volume and said, what's the minimum surface area? So instead of here, let's do the opposite. So I'll give you a perimeter. Let's say you have, I don't know, 48 inches. You have 48 inches of that metal that goes around the outside. And so what you want to do then is max the area out. And the problem is going to be real similar in the sense that you've got to use both equations. And so kind of notice this equation up here is P as a function of W and H. That's not good. And this is A as a function also of W and H. That's not good. I need A just as a function of W, or A as a function of H. I don't want equations that have two letters on the other side. And so can you make a substitution like we did last time? Because we're asking about the maximum area, it should make sense to you that it's the area equation we're going to take the derivative of. It's just that we can't take its derivative very easily now if it's got W's and H's in it.
Not that either way it's going to be fun, but if we plugged in the 48 for the perimeter equation and solved for H, then we would have all W's.
That's right.
Not that that's going to be any more fun, but...
No, well, you don't really have any choice. So you're right. If you're stuck with a limitation of 48 for the perimeter, and this is the perimeter equation, then that equation is solvable for W or for H. So I can replace one of the letters in the green area equation. Which one looks easier to you? They both work. Well, I only see one h up here, and then this just has an h. It seems pretty easy to solve the bottom one for h, and then there's only one h in the top equation, whereas there's a w and a w squared, and so I might be wrong, and I genuinely mean that. I might be wrong. This might not be the easiest, but it's not terribly hard to solve. If I subtract those two terms from the other side, and then I have 2h left over here, and then I just divide by 2. Then there's what h is equal to.
All right, I have a question for solving that.
Sure.
Could you move everything over, like, so move w and move 2h over, and then multiply by 2 to get rid of the 1/2?
Yeah, you could multiply the top and the bottom by 2 because we have fractions over the top of fractions. So before I plug it in, if I decided I think I'll multiply by 2 over 2, so that this becomes 96 minus 2w minus pi w.
Just to get rid of the fractions.
I kind of agree with you. I think that looks a little bit nicer. I don't want fractions over the top of fractions. So then I can say, all right, area now equals w times h, which is this lovely disaster. Plus pi over 8 times w squared. So there we have it. That's kind of the key place we've got to get. We have a now as a function of w. Again, I wouldn't have cared if it was a as a function of h. It's just that I only have two letters now. I have a and I have w. So if I take the derivative of this and set it equal to 0, then I'm going to find the maximum or minimum. Well, maximum or minimum what? Well, area. I'm going to find the maximum or minimum area. And I'll know what w produces that. I'll know what the width is that actually produces that answer. Let's see if we can hustle and finish this before we run out of time. So again, I can do algebra to this before I get started, and I don't like the fact that this is w times this, and so I really would like to distribute w to get rid of all the multiplication. Otherwise, that's some big nasty looking product rule. So if I do that, let's see, 96 divided by 4 is 24, so I'd have 24w, and then I'd have 2w squared over 4, which would be 1/2 w squared, I guess. And then I'd have minus pi w over 4, minus pi w squared over 4, minus pi over 4 w squared, and then plus pi over 8 w squared. Maybe you look at these and say, hey, I think I'll add those together. They're both the same terms. Or maybe you notice all three of those last terms have w squared in them, and you could just factor the w squared out and have just one big constant in front of them. There's more than one way to do this. Let's see, pi over 4 would be 2 pi over 8. Pi over 8, that'd be minus, am I doing that right? Pi over 8 w squared. So I'm thinking this is the equation I want to take the derivative of. That seems easier to me. So now I can go get a prime. Derivative of 24w is 24. Derivative of 1/2 w squared is just 2 times 1/2 is 1. It's just minus w. And 2 times pi over 8 is 2 pi over 8 or pi over 4. And so what I'm concerned with is, when is this equal to 0? When is there no change? That makes maximums and minimums. And so if I add the w and the pi over 4w to both sides and realize they both have w, so I could factor a w out, don't lose the 1 as a placeholder, then I can actually say, this is kind of interesting, I could say w is equal to 1 plus pi over 4. And again, you might think I don't like fractions over fractions, so I'll multiply the top and the bottom by 4. So then I'd have 4 plus pi. So that's kind of cool that you can get it exactly right if you want to. But again, that isn't my problem with this. Is does that help you build the window? No, you got to turn that into a decimal, or you have no idea what that number means. So 96 divided by 4 plus pi is approximately 13.44, and that was inches in this case.
We just have to go back and then plug this in for the equation to get your L, though, right?
Yeah, and I think
It only gives the width.
In the real world, this problem would be, you know, find the width and the height. So in our case, because we had a W, we found the width. And if I go back to some of the different equations that I've had, doesn't that one right there allow me to plug W in to get H? So then I would know all the dimensions I needed. And so, yeah, it feels like I'm not done unless I do that. I mean, I sort of see we're out of time here, but. So I will say, in the interest of time, hence H is approximately, so 96 minus 2 times 13.44 minus pi times 13.44. Get an answer, divide by 4. I got 6.72. Anybody notice anything interesting about that number?
It's about half.
About half. That's not a coincidence. That's the case again. Quick parting shot, just because I think you'll think this is interesting perhaps, but I will go over to my other screen, pull up my architectural drawings, pull up Pallotta. Would you live in this house? Shoot, how do I rotate? I can't remember. Can only rotate clockwise.
PDFs.
Would you live in that terrible house even with that ugly Norman window right there? Notice
It fits the style.
Yeah, it doesn't look bad on this one. I mean, he's got Gothic rock on it right here, and
yeah, sweet.
Notice the top of these windows are not half circles, but they are circular. So that's kind of even worse. So all the rest of these are arches, but they're not half circles, and that's true of this one over here too.
Yeah, this isn't really my style.
Yeah, suddenly Norman windows aren't so bad, are they?
looks like a ski lodge kind of.
Yeah, this is in Jacksonville, where I live. The foundation's poured, and they're starting to frame it. Now.
Yeah, it's just not. I like older style houses, like ranch style. It's more my speed. The Gothic rock on the outside is not for me.
Mm-hmm. Yeah, well, it's a good thing because that's an expensive decision. So my advice to you would be do all of the 4.5 assignment tonight. The good thing is tomorrow we're going to do a project where I'm giving you a maximum minimum problem. It's really a neat one. It's challenging algebraically. It's challenging based on calculus, and it kind of has a neat simplistic problem, but it's amazing how sort of complicated it is. So again, we have the whole day to work on it together. So during the day tomorrow, you can ask me questions about your homework assignment anytime. But I would say you need to be good at this because this project is, well, it's a project. It's not just another assignment. It's not just a simple assignment question. It's project. It's too complicated to be just considered an initial problem. And so you have 3 or 4 days to work on it. You don't owe it to me till Sunday night. It's already up. You can actually go, let's see. Yeah, it's up. You can go in there and get it right now. It's after the 4.5 assignment in My Open Math. And begin kind of playing around with it if you want to. But the main thing would be good at this, like be good at the My Open Math 4.5 assignment before you take on this project, because the project will probably be too hard. And if you can't go back, and I've done 6 examples for you in the last couple of days, and if you can't go back and start to draw them together and say, oh yeah, there's a commonality. Every time I'm finding the equation I'm trying to maximize or minimize, I'm taking its derivative, and then I'm setting it equal to 0 and solving it. If you can't see the commonality in all those questions, this is really hard. But you should be impressed at the magnitude and difficulty of these, because everyone is really different, and they all draw on, at least the kind of the neat geometrical problems, they all draw on different kinds of questions or different kinds of geometry knowledge that you have at one time had but have to get back. And it's a big ask, I guess is what I'm saying. But this is one of the neat takeaways of all of what calculus accomplishes, and I think you can see that in a couple of the problems that I did, but they're all kind of neat in a sense. So we will pick it up there tomorrow, and we'll have all day just to kind of play with those problems tomorrow. Stay after if you like. Otherwise, I'll see you then. See ya.